Vale. Buenas tardes. Soy Eduard Cabé y ahí al otro extremo, Alexandre Debord, somos del Iaac, del Instituto de Arquitectura Avanzada de Cataluña. Hemos venido de Barcelona para presentar este proyecto que veréis fuera. El Iaac es un instituto de arquitectura en Barcelona que trabaja mucho con las nuevas tecnologías. Dentro de ello, un programa que lideramos que se llama el OTF, Impresión 3D para la Arquitectura, en cual desde hace 7-8 años desarrollamos impresión 3D con tierra con el objetivo de llegar a una nueva arquitectura. Entonces, trabajamos con tierra, este material que tenemos por debajo de nuestros pies, un material que es ecológico, un material que es kilómetro cero, un material que permite de trabajar in situ, entonces de enlazar con un contexto local. Y trabajamos con la impresión 3D, esta herramienta muy nueva de la cual habéis visto mucho durante el día, pero que nos permite de diseñar y de construir de una forma distinta, potencialmente incluyendo en un proceso de concepción y de construcción criterios muy precisos relacionados al clima, a la estructura, hacer una arquitectura performativa que puede tener su cierto nivel de libertad a la hora de la concepción y de la construcción. Desde hace unos meses ahora estamos hablando con la Bienal, con Joan, con Gemma, que nos invitaron para trabajar una pieza que yo no voy a describir, pero os describiremos en un momento. Entonces, para nosotros ha sido la ocasión de hacer un trabajo colaborativo con la Asociación de Ceramistas de la Bisbal. David, no sé si está afuera, está ahí, con quien hemos tenido un intercambio importante para entender este mundo de la cocción, que a priori nosotros no conocemos. Y hemos llegado con esta pieza que es realmente un experimento que se está haciendo ahora mismo para ver hasta qué punto podemos cocer una pieza impresa en tierra que podría ser un elemento arquitectónico. Antes voy a pasar en un momento la palabra a nuestros estudiantes porque no os lo he dicho, pero el OTF es un programa académico. Trabajamos con un grupo de estudiantes, es también un programa de investigación, en lo cual tenemos la suerte de colaborar con un equipo bastante grande. Somos unos profesores, pero también trabajamos, por ejemplo, con una ingeniería en Barcelona, con BAC, trabajamos también con consultantes a nivel climático, a nivel de simulación de fluidos, por ejemplo, también a nivel de la maquinaria que desarrollamos. Y aquí hemos venido con nuestro equipo más íntimo, más cercano, donde ahí al lado veréis Ashkan, que es nuestro asistente en el programa, Kunal, que es nuestro experto en fabricación, y Elisabetta Carnavale, que colabora con nosotros para todos los asuntos de materialidad y también del desarrollo sostenible. Entonces, bueno, voy a pasar la palabra a los estudiantes. Ellos os harán, bueno, el grupo es increíblemente multicultural, digamos, nuestros estudiantes son de todos los lados del mundo, entonces por esto os harán la presentación en inglés ahora, que será una presentación muy visual donde tendréis acceso a mucho contenido a través de la pantalla, pero después de la presentación luego iremos alrededor del objeto y ahí podremos tener conversaciones más cercanas con los estudiantes, pero también con nosotros en castellano si necesario.
Penso que lo has dicho todo, Eduard, bravo. Solo añadir y repetir el placer que fue de hacer esta colaboración con todo el grupo del Terracotta Biennal, la Asociación de los Ceramistas, también para Argeles Escolares, que nos ayudó desde la primera a encontrar el buen material para poder imprimir, y este experimento muy arriesgado, que acabó siendo lo que veis fuera, para nosotros un gran placer de colaborar junto con los alumnos, junto con este equipo. Espero que dentro de esta presentación podrán ver como este gran descubrimiento que toda esta herramienta al final nos permite explorar cosas más técnicas, pero también de una manera más creativa, y un placer de volver a ser humanos, ¿no? Hablamos siempre de máquinas, de material, pero al final lo que descubrimos aquí es todo el grupo de gente creativas y con ganas que hemos encontrado aquí. Entonces, muchas gracias a todos y ahora dejamos las palabras a nuestros superalumnos. All yours. Thank you very much.
Buenas tardes. Good evening, everybody. My name is Tapiwa from Botswana and Zimbabwe. We're here to introduce to you the 3D printed architecture course that we're doing at the OTF. Before we proceed, it would be great to introduce all the colleagues, the people that my fellow colleagues, the people that I'm working with. And I'd love for you guys to just raise a hand so we know where you guys are at. We have Bruno from Brazil, who's at the back there. Francesco from Italy, also at the back. Brenda, who is from Brazil. There she is, at the back. Zach from France. Nita, who's my colleague here with me, she's from India. Roshin, who's also from India. Tekle from Ethiopia. Lynette, who is not here with us, she's from Kenya. Louis from Mexico. And Timur from Kazakhstan. A special thank you, of course, to everyone who has made this possible.
And you? Where are you from?
And myself, I said at the beginning. I'm Tapiwa from Botswana and Zimbabwe. So, as I said in the beginning, we're here to introduce the topic of 3D printing architecture with clay. And the first question we want to know is, what is the potential of 3D printing architecture with clay? So what we see here is a project from the OTF, Iaac, which is the Terra Performer project. In terms of the potentialities, this is an example of a house done in Italy where the material was locally sourced. So in essence, clay provides a very local, environmentally friendly and sustainable potential for creating housing. With the goal of designing a chimney prototype, we started to look into the issues that could arise and compare methodologies for the firing process with the traditional ceramic firing. Now, in traditional ceramic firing, you have the kiln, which solves the issue of the ambient temperature that would cause cracking for the fired object. In terms of the chimney, however, or the chimney prototype rather, firing without a kiln would mean possibly creating a fire from the inside of the chimney. Due to ambient temperature, this would cause cracking, which would be problematic. In the context of architecture, we are looking into where are they doing this. An example is in India, where they use firing to increase the waterproofability and provide mechanical resistance. However, as you see in the third image, you do get cracking due to the firing because of the ambient temperature differences. In this case, they have put ceramic tiles, so it doesn't necessarily affect the structural integrity. And this is where 3D printed architecture come in. So 3D printed architecture allows us to create a cavity, all the holes that you see here in the image. And this is printing of the Terra Performer project in Iaac. The cavity, in our case, with printing the prototype for the chimney, allows us to have two layers. And these two layers, which you see on either side of the chimney, would create the place where we could that could perform as a kiln. The outer layer becomes a sacrifice layer because it responds to the ambient temperature. And the inner layer is where our chimney would be. In between is the cavity, which we've gone into great lengths to understand, so we could design a chimney that allows for even distribution of heat throughout the cavity. We looked at different topics, or we're looking into different topics, in order to understand the material, the machine we're using, as well as performative aspects of our chimney in order to have a good final product. Now, you might wonder why we're choosing to work with clay. Well, first and foremost, we have 1.6 billion people who lack adequate housing currently, as we see in the first image. And clay housing for a long period of time has been used, and it offers a material that we can find beneath our feet. We also have the issue of CO2 emissions, with buildings contributing to 36% of CO2 emissions. Clay offers a low embodied energy material and allows the building material to be born or excavated from the site. And what is clay? So clay is a binding material and has a 3D molecular structure that reacts differently to water and can be molded and turned into different forms when it is processed. It has low embodied energy, as you can see, comparatively to other building materials that we use currently. In architecture, we use clay in different ways, such as rammed earth houses or as pure clay in itself. We also fire clay to produce bricks and produce ceramics as well. There's also the opportunity to create mud bricks, compressed mud bricks, as an option in architecture. Clay can be found when you dig 30 centimeters below the Earth's surface, and it's found more or less all over the world. And what we did, or what we're doing, is trying to test and come up with methods of how can we test the clay on the site. We're starting off with a hand wash test. So with the hand wash test, you find that if you try to wash the clay off your hand, if it sticks to your hand, it shows that there is a certain amount of clay present in the earth. The second test is the bottle test. With sandy soil or sandy earth, you find that the sand particles will all float to the bottom. Organic matter will float to the top. And if there's clay present, you'll find that the water stays a little bit murky. A third test is the cigar test, where you roll a cigar, you push it over a table slowly, and measure the length of the cigar or the clay that has broken off. So the longer that it takes for the earth to break, the more clay is present. Fourth test is a matrix where we mix clay with different amounts of sand in order to test, in the context of 3D printing, how well the material extrudes from the nozzle, how well the layers stick together, how well they keep their shape, and how minimal the shrinkage and appearance of cracks are in the final extruded layer. We do the same with water, where we try to understand how much water works best with clay, and the same with fiber as well. How much fiber do we need in order to create a well-adhered material? Lastly, we do clay and water compaction, where we add certain amounts of water with different types of earth in order to understand how earth can be formed in different molds when we use specific tools like compression or don't use specific tools. We always bring this back to the context of architecture, trying to understand how can this work in terms of construction, in terms of openings, roof overhangs, plastering, etc. In conclusion, with clay, we find that 2/3 of the clay combined with 1/3 of the earth, or rather the clay, combined with 1/3 of clay, rather earth and clay, is the perfect sort of combination to have. In terms of water, increasing by 20% normally gives us the best result, but this is subject to the clay because clay always reacts differently. The clay fiber mix, we know that having 50% of fibers is more or less the best composition to have a well-extruded material. So we have machinery in 3D printing, and we try to understand what types of machines do we use. We have different types, different scales that allow us to prototype and print on site. Why do we 3D print is in order to understand the material behavior and structure to be able to advance in the construction industry. This is an example of a project done by the OTF as well, where they were able to print on site. How do we understand the machine use and capability? Is through different methods from mixing, machine setup, through to extrusion. We look at 5 different topics, such as machine speed, to see, and we concluded rather that when you print the first layer slowly, you get a good overall print of the geometry that you're trying to produce. In terms of retraction, in order to get a well-finished product, you need a minimum time of retraction from the start of the print to the end, so the seam is nice and clean. The tool path direction, we found the spiral connection is best when you start the print and you end. The spiral connection is best. And in terms of nozzle diameter, it works sort of congruently. The bigger the nozzle size, the larger the print of the layer. Lastly, we found a 2:1 proportion. So for every nozzle size, you would create a layer height that is half the width in order to achieve a good print. And these are the conclusions we made in terms of material. So when we understand the matter or the material really well and the machine, we're able to create projects such as these, which is a project that was also worked on at the OTF, and add structure as an additional layer to the material. Regarding structure, we want to understand the way that by prototyping, we can understand where the project could fail, the geometry could fail, and we are in the process of using experimental digital tools to try to predict these failures. In terms of methodology, we as we said, are doing these processes in order to look at different topics and analyze them according to these digital tools we present. So we do that by picking a topic, creating a catalog, and testing with different analysis tools in order to predict this failure. In terms of center of gravity, center of gravity is one of the parameters that we look at. Inclination as well. Here we see that the red means it's inclining too much, so it might fail at this point, as well as same context in the global center of gravity. If it's moving out, it becomes problematic and could fail. We look at local inertia as well, which is how it could fail at a certain point to affect the structural integrity, as well as how the geometry works in tension and compression. Global inertia, this is how the overall object might fail or succeed. And in compression, we have realized that the more material you have, the more the less stress the object is under. In terms of cantilever, all clays behave differently, so you have to understand the clay in order to know how it could behave. You'll see that there's a lot of red in this because clay is a compressive material that doesn't work well in tension. So these are the conclusions we're able to make in structure, and we're able to then inform our design process and produce surfaces and facades such as these, where we understand the structure and are able to create housing in a sustainable way suitable for the masses. One of the performative criteria that we looked at was the thermodynamics. So thermodynamics, we wanted to understand in the context of our chimney, between these two layers where we have the cavity, how the heat will flow through the chimney. And how do we ensure that the chimney fires evenly? Because if we have the fire source at the bottom between these two layers, it means it will obviously be much hotter at the bottom and get cooler as the heat flows through to the top. So this is where the CFD analysis comes in. First, to simplify the process, we unrolled the chimney into a flat surface. And we looked at different types of connections between these two layers in order to understand how the heat would then be distributed throughout. Regarding the length of the connections, we found that the dark gray represents that the heat flow is moving slower through the cavity. And we find that the longer the connections, the slower the heat moves through the cavity. When we have more randomized connections, the heat stays in the cavity for longer. When we have high density of connections between the two layers in the cavity, then the heat also stays in for longer. When we have a 90-degree angle, we slow down the velocity, so again, the heat stays in for longer. And when we have directional angles, the heat gets directed according to the angles in the connections between these two layers in our chimney prototype. Groupings as well was something we are looking at. And in terms of groupings, the more connections that you have, then the more the heat, again, stays in our cavity. So these are the conclusions we were able to make to inform the design of the prototype.
The main design, the objective is to design a catalog for the final chimney with two layers connected. Thanks. Yeah. So the connections rely on tangencies to ensure the cavities between the two layers meeting at a point, and it also creates a very smooth direction for a clay to extrude while printing. And after that, we have created an array of one period of flow plan of the chimney, and the period has been arrayed to form a complete flow plan. And then you eventually loft to the height required. So the first step is to design a segment of the chimney and the two layers to make sure the outer layer and the inner layer are connected and they're touching at a point to define the size and the shape of the cavities. So you have two different plans, one at the base, at the bottom, and one at the top, which is around 2 meters high. And you have simple, medium, and complex connections to understand the complexity of the form and the cavities as well. So as you see in the lofter one as an example, as a full surface, how the connections change at different heights from like 50 centimeter to 100. And then at the 100, it's a singular cavity. And then at 150, it's to a segmented cavity with the help of tangencies. And as we focus more on details which are required to achieve the final design, the objective is to create like sections and consider the conclusions we have gone through the workshops. This is just a sample geometry, how we analyzed and studied the chimney and how we designed the chimney. So the geometry has been unrolled as a 2D surface. And the first element is the entry detail, the openings of the fire distribution, how the dimensions of the heat source and the structural behavior of the material has been considered to design the opening of fire, the heat source. The second is the perforations. The chimney within has perforations within to allow the heat to flow within the chimney to have an equal distribution of heat throughout the chimney from the bottom to the top. And the horizontal connections, the connections of the outer layer and inner layer have been tested with different lengths and angles considering the material consistency. The more the angular connections allow the direction flow of the hot air in a more spiral direction. The vertical connections, the joinery detail of the chimney vertically has been made on all four pieces to make it easier to stack the pieces together. So and the final conclusion is considering the angular connection, the heat source, and the perforations, they have been implemented in one final design. And about the final chimney, which is a phoenix. So the goal of all the accumulator research analysis is to design the chimney that will be fired here at lab as well.
It's being fired.
It's in process. So the unrolled surface, as you see, the 2,000 millimeter is the height of the chimney. And the heat source have been implemented on the surface, the two heat sources, and the connection at 6 different levels at a certain angle, which allows the direction of the heat, and the openings and the deflecting wall. So the deflecting wall helps the fire to indirectly enter the chimney, so it doesn't affect the inner layer. And have it doesn't help the chimney creating the cracks if it has a more direct heat produced onto it. So with the analysis of the Z velocity, as you can see how the air flows within the chimney, how the connections direct the flow inside the chimney. As the panel is rolled with the connection which connects the base curve and the top curve. This is the final piece of the chimney which allows us to give at which angle you have the connections. At the horizontal and the vertical unrolled section. And you see the plan of the two layers, the inner layer, the double layer, and the outer layer, and they are put together to form the final geometry. So these are the basic dimensions of the chimney when we had considered and been designed accordingly. So the chimney has 3 layers. So one is the outer layer, which acts as a sacrifice layer, and the second layer is the deflecting layer, which directs the heat source into the inner layer. So the inner layers is where the main chimney is, where you have the perforations, which lets the heat flow within the surface. In the full section, like here, you can see how you have the connections at different levels, which is holding on. I'm very sorry. So it's holding on to the two connections, like to define the cavities, which the cavities helps for the heat flow throughout the chimney for a equal distribution. And you have the joineries where you see at 3 different levels, which allows the connections, each section of the chimney to be placed on top of each other. And the perforations allow the heat to flow within. And here you can see the section at different levels as the cavities and the joineries change at each section. So at the bottom you have more like a singular cavity at 400 millimeters, And at 850, it has connected at 4 joints, and it has 4 cavities. And then it creates at 1,375, it's again a singular cavity with a minimal support. And at 2,000, it ends up being a one singular cavity. So it's the final design have been prototyped like with 1:5 scale to understand the connection, the openings, and the material stability. And also the final model have been fired to test the outer layer, whether it's gonna crack or does it hold, and the material stability and as the structure as well. And the final process, the production, the final design has been produced at 1:1 scale on the KUKA robot, as you can all see out there. And how did the process go? So first we have a dry mix, we have additives and a clay itself. We weigh the dry mix, and then we add water and mix it well. And with the help of pub mill, we ensure that there are no air bubbles within the mixture, and they are filled into the cartridge. And then they have been sealed and stored well so that it doesn't expose to the air and let it dry. And then we load the cartridge into KUKA, and we do the extrusion test to ensure the air pressure and the required air pressure and the material consistency for the printing as well. And then we start the printing. And after the piece has been printed, we move to a dry room to make sure all the water is evaporated and it's completely dried. And then we assemble the pieces to test if all the pieces fit in together, and if it is required, then we did a bit of sanding, so to ensure like after it's dried, all the pieces like stick together. And then we transported all the pieces to lab as well, and then we lifted them, and then we assembled them, and then the firing. And as you see, the dry mix, the material, the mixture itself contains a clay called lila and an additive of N700, HMP, and lingosulfonates and cellulose. And a water has been added around 1,800 ml. And they have been mixed well, thoroughly, to make sure there are no lumps or any dry clay left. And then the cartridge has been filled with the help of pub mill, where it ensures that there's no air bubbles in, and every cartridge is 1 meter long. That is what fits into the KUKA, and approximately 28 to 30 cartridges were prepared for the entire the chimney. And the final print was around 1.75 kilometer approx, and we needed around 289 kilograms of clay, and it took 4 days to print the entire piece altogether. And as you see, the 4 sections, the top one, the second, and the third, and the fourth is the base. And here is where all the 4 pieces were printed, and as you see, all the 3 pieces have been drying and dehumidified. And as you see, all the pieces have been stacked at lab as well here. And the firing has been started in the morning, and it's still in process.
In closing, would like to introduce, thank you. In closing, would like to show you a video that the team worked on. So please do enjoy it.
Firing completes the transformation of clay from a fragile material to one that is resistant and impervious to water and time. Can a building be fired? Can an object be its own kiln? Phoenix is an experiment examining how 3D printing allows the development of an architecture built with earth that can be fired to improve its resistance and durability. The initial geometry is defined by two layers that create a continuous cavity within the structure. An external shell is added to guarantee that the internal wall is encapsulated with heat. For the firing process, torches are positioned at the bottom of the structure. The airflow produced by the flames appears as the first gesture that determines the connection between the two walls. The orientation, size, and position of the connections influence the dispersion of heat throughout the walls. The continuous cavity is designed to guarantee stability, geometric union, and homogeneous distribution of heat. In addition, the inside wall is drawn with openings at the bottom to allow heating of the interior of the structure. From the connection in 2D, a landscape is created and later projected onto the original geometry. The inner wall becomes the final chimney, while the outer shell is designed to be sacrificed. Clay is mixed with additives to increase its structural performance, ease of printing, and to aid with the firing process. Spacers are placed in every first layer printed. This creates gaps later used to position the straps necessary for final assembly. For fabrication and ease of transportation, the structure is divided into 4 pieces of the same weight.
Un gran merci a todos. Os invitamos a venir a ver y a hablar con nosotros alrededor del fuego, que hace más calor, y de la chimenea para ver las cosas, y ahí podremos hablar. Muchas gracias.